All right, so as per usual, we are going to start with our low frequency analysis. And our circuit of interest in this case is this guy. So here's our input voltage. Our sig. Cn. And then we have some gate resistance here, RG. Here is a source resistance, RS. Coupling capacitor for our output. So I'm going to call this C out. Here is V out. And then VDD and VDD. Okay. So this looks extraordinarily similar to our fully biased source follower, except that, again, we have some input capacitance here, which is going to cause some sort of frequency response. And then we have an output capacitor here, which actually, as it turns out, isn't going to cause any issues because it's open circuit. If we were to connect a load to this output capacitor, then we would be completing the circuit and giving ourselves a path to ground. So we'd have a voltage divider at the output stage. But with this guy open circuited, it's not going to really mess with anything. And I'm going to show you exactly why it works out that way. I'm not just going to go on faith here. Okay. So what I'm going to do for this analysis is subdivide the circuit effectively into two stages. I'm just going to call this node X so that our transfer function H low of S will be Vx over Vn multiplied by V out over Vx. So we're just breaking it down into easily digestible parts. Everything to the left of the red dashed line represents the Vx over Vn portion. Everything to the right of the red dashed line represents the V out over Vx portion. Yes, sir.
What's the subscript on the R? The upper one?
G, because it's connected to the gate. So we have an R sig signal resistance, RG between the gate and AC ground, RS between the source and AC ground, and then an input capacitance, which couples our input signal to the DC operating point of our amplifier, and an output capacitance, which effectively isolates the output voltage from influencing the behavior of the DC operating point of our amplifier. Okay, so let's talk about the Vx over Vn portion. Hopefully this is fairly obvious, but we have a voltage divider. Surprise, surprise. It's kind of all we ever have if we have any. Okay. So our transfer function for our voltage divider, we're going to have Vx is equal to Vn times stuff. And Vx is effectively just going to be the voltage drop over our resistor RG, as we're going to treat VDD as AC ground in our small signal analysis, right? So that means that we're going to have a ratio of RG divided by R sig in series with the impedance of the capacitance Cn plus RG in our denominator. So I'm going to have this R sig plus 1 over S Cn plus RG down here. And from this, I can say that Vx over Vn. So I'm going to do a very small amount of manipulation here. I'm going to multiply through by a factor of SCN over SCN to get my fractions out of my fractions, as I tend to do. And so that's going to give me SRG CN in my numerator and 1 plus S R sig plus RG CN in my denominator. And we now have enough information to actually locate a zero and pole already, right? For the remainder of the circuit, we're effectively just going to be analyzing this bit, right? So let's say that I have my voltage Vx here connected to the gate of my transistor. My drain is tied directly to AC ground. Here I have my resistance RS. Here I have my capacitance C out. And this is my voltage V out. So I've just truncated everything to the right of the red dashed line as something that I feel will be pretty easy to analyze. So how I'm going to approach this is I'm just going to use the small signal model. I know that this is extraordinarily similar to what we saw in ELEN 335. The only real difference here is the presence of that capacitance C out, which might have some role to play. So just to be on the safe side, we're going to go to our small signal model and rederive things here really quick. So here's my voltage Vx, and it sees at the gate an open circuit. And then over here is the source. So here is VGS. My drain node is ground, so that's this guy down here. Between the drain and the source, I should have my dependent current source, GM VGS, where the current is directed as flowing from the drain to the source. We're neglecting channel length modulation as we have in all of these discrete problems. My resistance RS occurs between my source and my ground, which is my drain. So I'm just going to put RS in parallel here. And then lastly, I have my capacitor C out. And actually, let's call it by the impedance 1 over SC out. And then here I have my output voltage. So let's start with the obvious question. Is my small signal model correct? Anything seem particularly weird? So my input voltage to this system Vx is between my gate and ground, or excuse me, my gate and ground, where the drain terminal is at ground as well. So that's why I'm calling this whole bottom node D. Because I have an NMOS transistor, there should be a current source between my drain and my source, with the current flowing from the drain to the source, given by GMVS. My resistor RS is between the source and ground, and my capacitor C out represents an impedance between the source and the output node, where the output node is a nodal voltage measured with respect to ground. Okay. So our analysis here, using Kirchhoff's voltage law and recognizing that no current is going to be able to branch off and flow through our capacitor, we can say that VGS is simply Vx minus Vout. Is everybody okay with that? If we use Ohm's law, we can then see that Vout is simply GM VGS times RS, because all of our current GM VGS has literally no other path to ground other than flowing through that resistor RS. And Vout is simply the voltage drop over resistor RS, since there can't be a voltage drop over Cout. All right, so from here, I can simply substitute in my first relationship. And so that's going to look like GM RS times Vx minus Vout. And now what I'm going to do is simply move all of my Vout terms to the left-hand side of the equal sign. So that's going to give me a Vout times 1 plus GMRS is equal to Vx times GMRS. And from here, I can say that Vout over Vx is GMRS divided by 1 plus GMRS, which is exactly the mid-band gain, or the DC gain that we developed in 335 for a source follower amplifier. So everything to the right-hand side of the red dashed line does not actually contribute any poles or zeros, or doesn't contribute to the frequency response. So there's no dependency on what we'll plot these variable S. So from this, our low frequency response is simply GMRS over 1 plus GMRS multiplied by a factor of S RG CN over 1 plus S R sig plus RG times Cn. And because I'm running out of space here, from this guy, we can see that we have a 0 at 0 and pole at 1 over R sig plus RG times C. So that's our low frequency response. Now, just to reiterate here, if we had actually connected a loading resistance here, we would expect to see some contribution, because that would form a voltage divider at the output effectively. So expect something like that on your homework. All right, how did you guys feel about the low frequency analysis? This is fairly straightforward, nothing particularly wild or crazy. Yes, sir.
Why is it a voltage up over the capacitor?
Can current flow through this capacitor? Through this impedance? No, because it's open circuit. So if there's no current flowing through it, there's no voltage drop over it, thanks to Ohm's law. So V out is this voltage. Circuits one stuff. As always, that's what I'm going to tie stuff back to, because that's how my brain works from teaching that class so many damn times. All righty. High frequency analysis. Stop where I want you to stop, robot. Yes, sir. Yes, sir.
Is the homework going to be due Friday or Monday?
The common source amplifier homework is going to be due Friday. The next set will be due Monday, so that ostensibly you should have practiced everything that's you're supposed to know for the exam prior to taking the exam.
Sounds good.
All right. High frequency analysis. So our circuit of interest here will be the circuit that we just had, where all of our low frequency capacitors are treated as short circuits. So that's why Cin has gone away. And we'll see that C out has gone away in a moment as well. And our parasitic capacitances are now influencing the behavior of our device. So since we have an NMOS transistor, we are going to have 4 capacitors in play here. Between the gate and the drain. Sorry. We have our capacitor CGD. Between the drain and the bulk or substrate, we have CDB. Between the gate and the source, we have CGS. And then we have our resistor RS here between the source and the bulk. We have CSB, and finally we take our output voltage here, and our power supply is VDD. Okay. So a few things that we can observe here. The first is our capacitor CDB will not play any role because the right-hand terminal is tied directly to ground and the left-hand terminal is at AC ground since it's connected to the power supply. Right? Excuse me. So CDB is out, doesn't do anything. CGD can be treated as if it is in parallel with the resistance RG. So when I redraw it in a moment, that's exactly what we are going to do. Obviously, CSB and RS are in parallel, so I can treat them as a combined impedance ZS. So we'll do that. And we have a capacitor that's providing some sort of feedback and is linking our gate node and our source node CGS, which means our direct analysis is going to be a bit annoying. Okay. So I'm going to redraw this guy. For an arguably simplified look. So here's R sig. Here's RG. CGD. let's see. Our drain terminal is grounded out. Here we have that feedback capacitance, CGS. I'm going to call this impedance ZS, which is simply RS in parallel with 1 over S CSB. Sorry, I'm going to rewrite this bit right here in a simplified form as well, because we're going to wind up using that in a little bit. So this is going to be 1 over RS plus SCSB all to the -1. So effectively, all I'm doing here is treating these two things as conductances in parallel to get to this result. So this is my impedance, which is going to be the inverse of my conductance. Everybody okay with that?
Does CDB go away?
That's correct. Yes. So just to scroll back up here real quick, we have a ground on the right-hand side of CDB, and then we have an AC ground, VDD, on the left-hand side of CDB. So that's why it's not showing up in our simplified view. All right. So, oh, and I need to label my output terminal over here. All right. So I am going to call my gate node X and my source node Y. And we are going to approach this very similarly to what we did for our common source amplifier. I am going to effectively re-express everything to the left of this red dashed line with its Thevenin equivalent, just so I don't have to carry around so much baggage in our analysis here. So hopefully at this point, we should be able to figure out what the Thevenin equivalent of this is by inspection without redrawing it. So somebody tell me what that is.
DN multiplied by RG over RG plus RG.
All right, so that's my Thevenin voltage. Thank you. So let's write that down. V Thevenin is Vn times Rg over R sig plus Rg. All right. What is R Thevenin going to be? That's exactly right. R sig in parallel with Rg. You guys are capable of learning. Sorry, that was meaner than I intended. You guys are wonderful.
It was appreciated.
All right. So what I'm going to do now is I'm going to replace everything to the left-hand side of the red line with its Thevenin equivalent. And I'm going to represent everything to the right of the red dashed line with its small signal equivalent circuit. Okay. So that's going to look like the following network. I'm going to label it as small signal model. So I have my Thevenin voltage in series with R sig. So that's my Thevenin equivalent representation. Here is node X.
You mean R Thevenin?
Sorry, yes, R Thevenin. Thank you so much. That was a total brain fart. Thank you. Here's CGD. All right, so now I'm moving over to the right for the gate portion of my transistor. So I'm going to have my capacitor CGS over which a voltage drop VGS occurs. I'm going to have my current source GM VGS. My drain serves as a small signal ground, and then connected between my source, I'm calling node Y, and ground, I have that impedance ZS. And then my output voltage, V out, is the potential difference between my source node and ground, which is the same thing as the voltage drop over my impedance ZS. So are we comfortable with this small signal model? All right. So the first thing that I'm going to do here is I'm going to determine an expression for, I'm going to actually, sorry, I'm going to write a KVL equation, okay? And so I'm going to show you the path that I'm going to use here. I'm starting at VThav. And I'm going to ground this way. So effectively, I'm starting at the negative polarity terminal of VThav. And I'm going to say that V Thevenin is equal to the voltage drop over R Thevenin plus VGS plus V out. Well, in order to get the voltage drop over R Thevenin, I'm just going to arbitrarily say there's a current, and I'm going to call it IX. Okay. So applying KVL, we get V Thevenin is equal to R Thevenin times IX plus VGS plus V out. I'm going to call this equation 1. Are we okay with this representation? All right, the next thing that I'm going to do is I'm going to apply KCL at node X. So I have a current of IX flowing in. And then flowing out, I have the current flowing through capacitance CGD. And I have the current flowing through capacitance CGS. So let's start with the current flowing through capacitance CGS because that's a little bit easier to quantify. That's simply going to be VGS divided by the impedance. So VGS over 1 over SCGS is simply VGS times SCGS. I'm going to do something very similar here for the impedance of CGD, where I can recognize that the total voltage drop over capacitance CGD from node X to ground is just VGS plus V out. And I'm going to call this equation 2. Obviously, now I can substitute equation 2 into equation 1. And now I'll do it on the next page. 2 into 1 is going to give me V Thevenin is equal to R Thevenin times IX, where IX was S CGS VGS plus S CGD VGS plus V out plus VGS plus V out. And now I'm going to manipulate this very slowly, okay? So I have multiple terms that include the quantity VGS. And I have a couple of terms that include the quantity V out. And so I'm just going to write them as some coefficient times VGS plus some coefficient times V out. And so what that's going to give me is 1 plus S R Thev CGD plus CGS all times VGS plus 1 plus S R Thev CGD times V out. All this through. Well, let's double check the algebra here because I know that I'm likely to make mistakes. So the 1 for VGS obviously comes from this bit right here. Then I have an S from this bit and this bit. The RFF is being multiplied by both. I have a CGD coming from here and a CGS coming from here, so that bit seems legit. The 1 for V out comes from right here. And then I have an S times an RFF times a CGD times V out. So things algebraically seem to check out for me. Excuse me. All right. So I'm going to scroll back up. We're about to apply KCL at node Y. And so I'd like to look at node Y. Okay. So how I'm going to do this is the current flowing in is equal to the current flowing out. So flowing in, we are going to have a factor of GM-VGS. We are going to have a factor of SCGS-VGS. And then flowing out, we're just going to have V out over ZS, or V out times the admittance of ZS. Okay. So that's going to give me GM VGS plus S CGS VGS is equal to 1 over RS plus SCSV times V out. I can factor out VGS on the left-hand side, giving me VGS times GM plus SCGS is equal to V out times 1 over RS plus SCSB. And from here, I can then say that VGS is equal to V out times 1 over RS plus SCSB divided by GM plus S CGS. And I'm going to manipulate this a little bit. So I'm going to explain exactly what it is that I'm doing. Okay? I am going to multiply through by a factor of RS over RS to clear out my fraction. And then I am going to factor out GM-RS from my denominator. Okay. So the reason why I'm doing that is because I'm planning ahead and I know that I should expect to see a GM-RS in the numerator later on because that's a portion of my midband. Okay. So performing those two steps, again, multiplying the numerator and denominator by RS to clear that fraction in the numerator, and then factoring out GMRS from the denominator only, leaves me with V out multiplied by 1 over GMRS multiplied by a factor of 1 plus SRS CSB divided by 1 plus S CGS over GM. And I'm going to call this 4. All right. So now what I am going to do is substitute 4 into 3. I know. But what's that going to give me? Okay. VFAB on the left-hand side, everything in terms of V out on the right-hand side, I'm literally one step away from getting my transfer function. Okay? There's a method to this madness and ludicrous amount of algebra. So if I substitute 4 into 3, what I get is VFEV is equal to 1 plus S RFEV CGD plus CGS multiplied by 1 over GMRS times 1 plus SRS CSB over 1 plus S CGS over GM times V out plus 1 plus S RFEV CGD times V out. I'll call this 5. All right. So we're at a point where we can see exactly where our transfer function is coming from. Now I'm going to gloss over another page worth of algebra to get this into the right form, much like I did with the common source amplifier, so that we can get down to the meat and potatoes of how this particular circuits work. Okay, so effectively just rearranging 5 and then doing a good amount of algebra. What we get is that V out over V FEV looks like this. Excuse me. So we'll have GM RS over 1 plus GM RS, our midband gain, multiplied by a frequency dependent portion. And again, it's going to be one of those horrifyingly large fractions. S squared times RS RThev CGS plus CGD times CSB plus CGS CGD. This whole thing divided by 1 plus GMRS plus S times CGD plus CGS over 1 plus GMRS times RThev plus CGS plus CSB over 1 plus GMRS, close that bracket, plus 1. And then in my numerator, I have simply 1 plus S CGS over G. So we have another polynomial. What was that? Factor? Factor. Okay. All right. Sure. Yes. So we have an annoyingly large thing that we've known how to solve since the 8th grade because this is a second order polynomial, right? So by inspection, we can get our zero frequency rather easily. Omega Z is simply GM over CGS. And then if we call this bit A and this bit B, our pole frequencies are omega P1 is the absolute value of negative B plus the square root of B squared minus 4A all over 2A, and omega P2 is the magnitude of negative B minus the square root of B squared minus 4A all over 2A. So there's our direct analysis loop. So yes, you're 100% correct there. This is simply the ratio of V out over V in. For our full transfer function, Luke is 100% correct. We would need to multiply by a factor of RG over R6 plus RT. But this is a purely, it's not going to influence the frequency response at all. So that's why it doesn't matter in my determination of pole usage. You're absolutely correct that it does need to be there, but that's just a simple ratio of resistances, which is frequency independent. So for the overall transfer function, for sure, put it in 100%. Okay, so that was our direct analysis. It was annoying, as it tends to be really anytime that I have my input node, which is the gate of my transistor, and in this case, my output node, which was the source, coupled together. I'm not going to go through the steps here, but what could we do to approximate this and make our analysis easy? Really only one thing that we've talked about that will allow us to do that. Luke, what is it? That is absolutely the wrong answer. The Miller method, which would split this capacitor tied only to node X and another portion that's tied only to node Y. And the transfer function between X and Y is just our mid-band gain, GM RS over 1 plus GM RS. So we would pull a portion of CGS and multiply it by 1 minus K. And we pull a portion of CGS over to the Y node, where it would be 1 minus 1 over K. Right? And at that point, the input and output are totally decoupled. I hope you didn't spill like a couple of eyes or something like that. That's what it sounded like. Okay, that's not bad. Well, we're about to wrap things up. So you can clean stuff up. Anyway, so applying the Miller method here, which I'm going to ask you to do in your homework, would allow you to effectively analyze the circuit at node X to find the resistance connected and the capacitance connected, analyze the circuit at node Y to find the resistance connected and the capacitance connected, and then get your poles from that and be done with it. Right? So we've got the direct analysis, and I did all the math for you. I'm going to ask you to do the easier amount of math, which is using the Miller method to split that feedback capacitance up, and then in the homework problem, ask you to compare the results. Sound reasonable-ish? All right. So that is enough out of me for today. What we are going to do on Wednesday is we'll probably look at the differential pair first, because it'll take like a minute to say, yep, it still looks like a common source amplifier, so it behaves like a common source amplifier. And then we will do a cascode, which will be ugly. So, then we'll be done with this. All right. So, like I said, I'm going to go pop off to my office to eat a very quick lunch, and then send out some emails. From 2 to 5, I'm free for harassment. So go nuts.